So what is a Markov decision process? So Markov decision processes are used to model decision making, and they are an extension of Markov chains. So they're an extension because we add actions, so we allow choice, and we add rewards, so we give motivation. And Markov decision processes are defined as they are made up of 4 elements. So the first one is a set of states. So states we just showed in the little example can be here all the possible states that the agent can be in, and the set needs to be defined. Then we have a set of possible actions in each state. So in our case we had up, left, right, and down. And different actions can be available in different states, or all the same actions can be available in all states. Depends on how you define your Markov decision process. Okay, let's get another color. Then we have transition functions. So those are the transition probabilities. They're defined like this. The transition goes from state S to the next state, S bar I'll call it now, by performing one action. And the transition probability is then defined as the probability of ending up in state, so of the next state being state S bar, given that the current state is state S and the current action is action A. So what's the probability if I'm in state S and perform action A that I will end up in state S bar? So in our little example, I'm here, I perform this action, what's the probability that I will end up here? And if we have a deterministic environment, this can just be 1 for all transitions, but we can also have stochastic environments where we are not so sure where we will end up if we perform a certain action. So like if we're on the stock market and I buy a certain stock, I'm not so sure where I will end up after a week. So yeah, for stochastic environments, this is important. And then the last thing in our Markov decision process are rewards, which are what we learned from. So they are defined as, which reward do I receive if I'm in state S? I perform action A and I end up in state S bar. Okay, so let's do a little example. Let's say we have a robot vacuum and the robot can be in 2 different states. So the battery can be charged or the battery can be low. And let's say it's a really simple robot, so it can't distinguish any states in between. And in each state it can pick 2 different actions. So it can either go clean or it can go charge. Okay, and then we can define the transition probabilities for these. So let's say if the battery is charged and the robot goes to clean with probability of 0.8, it ends up back in the charge state, and with probability 0.2, we end up in the battery low state. If the battery is already low and we go clean with, let's say the probability is a bit lower that we still have a low battery, so let's say with probability 0.3 we end up there, and with probability 0.7 we end up in the battery charge state. And what happens here is the robot runs out of battery without going to the charger, and the human has to come pick up the robot and bring it back to the charger. So that's not so good. It kept vacuuming without going to the charger early enough. Okay, and it also has the option to go charge. So if the battery's low and it goes to the charger, it ends up in the battery charge state afterwards, and let's say it's always successful, so probability is 1. If it is already charged and goes to the charger, it ends up back in the same state, and also always successful. Okay, so now I already said if the robot runs out of battery without going to the charger, the human has to come and bring it to the charger, so that should be bad. So let's say we give it a negative reward of 3. And if the robot is cleaning, that should be good. So let's say it gets a reward of 1 in both states. So this is the definition of a Markov decision process. So now we can try to solve this process by finding an optimal policy. So when should it go to the charger? When should it keep vacuuming in order to maximize its overall reward? And so basically at every time step t, the decision maker, so the agent, in this case the robot vacuum, chooses an action A from all available actions in state S. So in this case, in both states, the same actions are available. We could also say that if it's already charged, the action to go to the charger is just not available, then there would be just one available action. And proceeds from state S to S bar with probability, with the transition probability, and receives a reward. Someone's writing. If you have a question, you can also just interrupt me and ask the question. Okay, so Peter asks, is the set of states limited to finite, countable, infinite, or continuous? So the set of states in this case is not continuous. So we have a finite set of states that we have to define, and so it is countable. And if we have, for example, continuous states, we need things like function approximators also to represent these states, and I'll talk about that a little bit later. Okay, okay, so it was already, yeah, exactly, like Leon said, this is now, first I'll be talking about tabular reinforcement learning, so we actually represent each state as a discrete state. Okay. All right. Yeah, feel free to just interrupt me if you have a question too. Thanks for everyone answering. Okay, and then we have the Markov property. So the Markov property says that the next state depends on the current state, but is conditionally independent of all previous states and actions. So the future is independent of the past given the present. And in real life problems, this might not always apply. So, for example, in the robot, whether it will end up in the battery low state might depend on how often it has already been in the cleaning loop in the battery charge state. So it's not just dependent on the current state, but this is the Markov property. And in some of the algorithms later, we can relax this property a little bit. But yeah, it is a property for Markov decision processes. Okay, and our goal is to find a good policy pi, which gives us probabilities for actions given states that maximize the overall reward. And usually we try to maximize the expected discounted sum of rewards over infinite time. Okay. And how do we define this sum? So let me just go up a bit. All right, so the expected discounted sum over infinite time. So we need an expectation over the infinite sum. So we go from time step 0 to infinity. Then discounted. So we have this gamma, which is our discount factor, times the reward that was received from going from state S to S bar performing action A. And that's it. So we discount the rewards to infinity with the action time t chosen from our policy pi. of the current state. And that's the expected discounted sum of rewards for under our policy pi that we're using. And this discount factor gamma is usually between 0 and 1. Usually we put it close to 1 in practice, and using the discount factor guarantees convergence, because if we have a loopy MDP, we could end up in having a sum that just sums up to infinity, and then we can't converge when solving this Markov decision process. So that's why we need this discount factor. And if we set a small gamma, we favor short-term rewards, so we favor immediate rewards over rewards further out into the future. And if we set a large gamma, we favor long-term rewards. Okay. And this sum can also be called the discounted return, GT. So we can just rewrite this real quick, the part that is inside of the expectation. So GT is basically taking the reward at time t plus 1 plus the discounted reward at time t plus 2 plus, okay, now we take gamma squared of reward t plus 3 plus, and so on until infinity basically. So we sum up to infinity of the discount factor to the power of k times the reward at time step t plus k plus 1. And k is the number of steps in the future from time t that we're at right now. And that means basically the discounted return GT gives us the sum of discounted returns received from time t onwards when following policy pi. And we can, instead of summing up to infinity, we can also sum up to the terminal state if we work with episodic tasks. Okay, and using this discounted return, we can now define a value of a state following policy pi. So how good is it to be in state S if I follow my current policy? And the value of state S is defined like this. So it's always defined under a certain policy. So it depends on how we're acting, how good a state is. And it is defined as the expected value under policy pi of the discounted return given the state that we're in. Okay, so how much discounted return do I expect when I follow my policy pi from state S? And to find the optimal policy, so we want to find pi star. We need to maximize this formula, so we take the argmax over all possible actions of the sum over next states and rewards of the transition probabilities. So given state S and action A, what's the probability of ending up in state S bar and receiving reward R? And then we multiply these transition probabilities with the reward that we received plus the discounted value function of the next state. And if we want the optimal policy function, this should actually be just S bar, not S star. And if we want the optimal policy function, we need to use the optimal value function here. Okay, so this is what we need to maximize to find the optimal policy. And let's just do a quick example for this. So let's say we have our grid world that I talked about earlier. we are in state S. Then we have S0, S1, S2, and S3 that we can end up in. And each of these next states have a value that we already calculated. So here those two are 0. If we go up, we have a value of 3, and down is a value of 1. And also in the next states, we can receive rewards. So here we don't receive rewards, but if we go down, we receive an immediate reward of 1. And to make it a little simple, so we have 4 possible actions, and let's say we are in a deterministic environment, so the probability for all of them is 1 if we select them. So here these transition probabilities are 1. Okay, and now let's calculate our optimal policy if we're in state S. So pi star of state S is the argmax over our possible actions. So what are our actions? We can go up, down, left, and right. And so we just said that our environment is deterministic, so the transition probabilities are 1, so we'll just write a 1 for all of these here. And then we multiply this with the reward that we received. So up is the reward of 0, down is the reward of 1, the other two are also 0, plus the discounted value function. So alright, so we have to say our discount factor is 0.9. So plus 0.9 times 3, because up we have a value of 3, then down we have 0.9 times 1, and to the left and right we have 0.9 times 0, because the value is 0 there. Okay. And then we can just calculate this. So this one would be 1 times 0.9 times 3, which is 2.7. Here we would get 1.9. Here we get 0, and here we also get 0. And the maximum here is, so the argmax over all possible actions is then going up. So under the optimal policy in state S, we would go up. And now I have a little exercise for you. So pay attention. Now my question would be, what is the optimal policy if we set gamma to 0.2? So do the same calculation. The only thing we replace is this part. So here's the formula for calculating the optimal policy. I just gave you an example for gamma is 0.9. Go into the breakout rooms and calculate the same thing for gamma is 0.2. Okay, welcome back everyone. I hope you didn't have too much trouble. By the way, if you don't have the question written down or forget it or have a question, just leave your breakout room again and come back to the main room. I'll have the slide open and you can look at it or ask me a question and then go back to your breakout room. Okay, but I hope you could talk about this a bit with your group. So here's the answer. So for the first, on the bottom, we can see what we just calculated. So for gamma is 0.9, up is the optimal action. But if we have the discount factor set to 0.2, I hope you came to the conclusion that now the optimal policy would be going down, because we have replaced all the 0.9s with 0.2s in the formula. The rest stays the same because value estimates are still the same, rewards are still the same, we still work with the same environment. But if we now have a different discount factor, we get new values. And so the question is, why is this now a different optimal action? So as I said earlier, if we have a low gamma, we favor short-term rewards over long-term rewards. And going down gives us an immediate short-term reward, but the value estimate is not so high. So the value estimate is only 1. If we would go up, the value estimate is 3. So we have a pretty high estimate for the future rewards we'll receive. So going up, there will probably be a higher reward after a few more steps. So if we favor long-term rewards, going up is better. So if gamma is 0.9, that's why up is there the optimal action. But if we just favor short-term rewards, we just want to get an immediate reward, then going down is better. And that's what is expressed with gamma being 0.2. Okay, so if you got this right, feel free to move your token 2 points forward, or if you feel like you only got it half right, move it 1 point forward. I leave that up to you to be honest with your group or whatever. I mean, you can also just move yourself up too. So yeah, and if you have any questions, let me know. Otherwise, I will continue.